Morning, everyone. We'll get started here. We're finishing up chapter 4, and then I think we actually I'm gonna get us to maybe lecture a little bit forward on chapter 5, just so we've got the basis for next week. And then one thing to note, your first test is on Monday, or rather Sunday to Monday. So please make sure you get that completed. There's really no reason for you to not get it done. So yeah, I don't want to get a message on Tuesday that you're like, oh, I forgot to take the test. Can you open it? My answer is officially no. So just make sure to take it, and we shouldn't have to run into that issue. So just looking at the syllabus.
Sunday, Mrs. Moore, I'm sorry, Sunday.
It opens up Sunday at 5 a.m. and it's open until Monday at midnight. Now you only have an hour and a half to take it, so it's not like you can just casually like take the test for a 2-day period. Once you've committed to starting the test, you've got an hour and a half to finish it, if that makes sense.
Yes, sure.
Okay, cool. Yeah, so you have one weekend day and one weekday, just depending on what works better for you. I've had students who like regularly took it 9 a.m. every Sunday. I have a lot of students that take it at 10:30 at night on that Monday. It doesn't matter to me as long as it's done before the midnight period. Okay. So real quick, looking at the syllabus though, this weekend is going to get a little bogged down. So you've got 2 experiments due and 2 of the associated quizzes due, and you also have 2 mastering chemistries due, and you have a test. So if you haven't started any of those, I would start some of that tonight. Give yourself an hour or 2 to start chipping away at some of this so you're not super overwhelmed. Next week, we'll be going over nomenclature. And again, I might try and lecture a little forward on that today. We'll see. Okay, so we left off, we were talking about ions in this concept that, the number of electrons within a material can change. So an atom can be either neutral or it can be charged. If we're dealing with, my internet says my internet is unstable. Is anyone having issues with my internet? You guys able to hear me?
Yes, just momentarily, Mrs. Henderson, you were going in and out.
Okay, it seems okay now. Okay, cool. So if we're looking at, let me pull something up. Calcium, which is in column 2. If it's in ground state, meaning it's not charged, we would write it like this, Ca with nothing in the upper right-hand corner. This lets me know that the number of protons and the number of electrons are equal to each other. If it's calcium, protons always have to be 20. If it's neutral, these 2 values should equal each other, right? The charge is the difference in these 2. If we're dealing with the charged version of calcium, calcium is in column 2, so it likes to form a 2+. The protons will still stay at 20, but the number of electrons will drop by 2. So we'll have 18 here. Electrons have a negative charge. So again, think of them as like negative people in your life. If you get rid of 2 of them, you will become more positive. The equation to calculate charge is going to be charge equals the number of protons minus electrons. So if you have more electrons, this is a negative value. If you have more of these, you're going to be negative. If you have more protons, you'll be positive. So we haven't really talked a whole lot about neutrons, but we're going to now. So a neutron, right, we've got our 3 subatomic particles, protons, electrons, and neutrons. Protons have mass and they're positive. Electrons have very little to no mass and they're negative. Neutrons have a mass, like a proton, but they don't have any charge. So you can get these things called isotopes. And that word is written right here, isotopes. An isotope is an atom that has the same number of protons, but its number of neutrons is different. Now, if I change the number of neutrons, again, what are the properties of neutrons? It has mass with no charge. So if I adjust neutrons, I'm going to change my mass, but nothing happens to charge. The charge stays the same. So you can add, or, I don't mean you, but, in the environment, there can be isotopes that have more neutrons, which will make the atom heavier, or they'll have less neutrons, which will make the atom lighter. It doesn't change the fundamental properties. Like, for instance, carbon 12 is got 6 protons and 6 neutrons. Carbon 14 is got 6 protons and 8 neutrons. It's still carbon. One of them happens to be unstable, but it's still got the carbon quality to it. So let's look at isotopes for neon. So when we go to our periodic chart and we see neon, which is number 10, that means that it should have 10 protons. But there's a variety of isotopes, specifically 3 isotopes. We've got neon 20, neon 21, and neon 22. Now, this is not written in the upper right-hand corner, okay? So this is not explicitly talking about charge. This is talking about the mass of the whole atom. Now, mass of your atom is going to equal the number of protons plus the number of neutrons. Why don't we include electrons in mass? Because they don't have a mass. I mean, they do, but it's so tiny, it doesn't affect the mass. So electrons have a charge change, but they don't affect the mass. So when this says neon 20, the 20 is referring to the number of protons and neutrons in the nucleus. If it's neon, you will have to have 10 protons. Like, that's what makes neon neon. So that's non-negotiable. But we're dealing with neon 20 here. So if I subtract out the 10 protons, the 10 remaining mass is going to be attributed to the neutrons. So neon 20 will have 20 protons. I'm sorry, neon 20 will have 10 protons, and it will also have 10 neutrons. So an equal number of protons and neutrons. Some people get in this habit of thinking, oh, the number of protons and neutrons should always equal each other. That is not the case, especially as we get heavier in the elements, the number of neutrons really starts to skyrocket. Neon 21, which is a heavier variation of neon, still has 10 protons. That is what makes neon neon. But because it's neon 21, it's slightly heavier. This has 11 neutrons. Neon 22 is the heaviest of the 3. How many protons? It better have 10 protons. That's non-negotiable. But the number of neutrons has jumped to 12. And in nature, there is a certain abundance of these isotopes. Some of the isotopes are more prevalent than other ones. So for neon 20 is the most prevalent of the isotopes. It's at about 90.48%. Now, don't get freaked out. I don't expect you to have all the isotopic percentages in nature memorized or anything like that. But it is important to understand this concept that, there are different types of isotopes, and they're in different percentages. Neon 22, which is the heaviest, that's the second most prominent. That's at 9.25%. And then neon 21 is the least likely to exist. That's at 0.27%. So looking at your periodic chart, you see neon, you see it says 10 at the top, 10 protons. And then at the bottom of your periodic chart, at least mine says the mass, or the number at the bottom, is 20.180. Now, if the mass is the number of protons and neutrons, shouldn't that be a whole number, right? Like, we shouldn't have half protons or half neutrons. So why is it decimaled? Why is neon's mass decimaled? It's because it's an average of all of these masses combined together, okay? So let me try and see see if I can pull back up that periodic chart so we can all be on the same page with that. That one doesn't have the masses. This one does. Okay. So like, this is what I'm talking about over here. So we've got neon, it's 10, that's 10 protons. And then the mass, this is the atomic mass. This is how heavy the atom is. The atomic mass is 20.18. And it's like, well, why is it a decimal? Shouldn't it be whole numbers? Protons and neutrons are always presented in whole numbers. The reason it's decimaled is because of these isotopes, because this is an average of each of the isotopes together based off their relative abundance. So have you ever like calculated your grade before? And like tests are worth the biggest percentage and homework's worth like not as much, and you have to weight it out or you have to average it. So, you know, oh, I've got 100% on homework. Yeah, but you have a 60% on the tests, and the tests make up 80% of your grade, right? So you have to weigh them out. So that's how we get to that percentage. And we're going to work on calculating that. Some other ways you can write isotopes. Sometimes they'll write it with the symbol here, and then the mass number for that given isotope in the upper left-hand corner, or the front left-hand corner, and the atomic number on the lower left-hand corner. So it looks something like this: neon 20, neon 21, and neon 22. And then they put the 10s on the bottom. I don't particularly like this way of writing. It seems a little redundant to me, because if it is neon, isn't it always in fact going to have 10 protons? Like, these two things are sort of synonymous with each other. Another way you may see it written is like this: neon with a dash 20. This is like the one I like the best. It's the most efficient. Or they'll write the whole name out with 20, 21. So the mass number A is always going to be the sum of the protons and the neutrons. So if I tell you, hey, I'm dealing with neon 20, how many protons and how many neutrons? You can easily tell me, well, neon has to have 10 protons, so the remaining number needs to be the neutrons. So let's go ahead and do that for another isotope. I want you to tell me how many protons and how many neutrons there are for, what do I want to do? Chlorine 35 and chlorine 37. Okay, so the two main isotopes for chlorine. Tell me how many protons you expect with that isotope and how many neutrons with that isotope. All righty. So this one shouldn't have taken too long. So we're just trying to determine, hey, how many protons and how many neutrons, protons and neutrons. So right off the bat, I'm going to just get the protons right. It's chlorine, it's number 17, so it has to have 17 protons, non-negotiable on the proton. This attaches directly to whatever the element is. The neutron is what's going to shift. Now, atomic number, so, or rather atomic mass, so this mass right here, mass, will always equal your protons plus your neutrons. So if we know the mass is 35, we know the protons are 17, what are the neutrons? There goes my internet again. Sorry, my husband's home today and he's stealing my internet for his architecture meetings. What does he think he is using my internet? All right, so we've got what, 37, we subtract the 17 and we get 20 neutrons for this guy. Okay, so it's not the same number of protons and neutrons. What do we have going on over here? Sorry, 35 minus 17. Where am I? 35 minus 17 should be 18, right? Yeah. I was calculating the other guy. All right, 18 for this one. This one is our 20. So definitely want to be able to do that. It's really simple math. It's more so just the concept of knowing proton will always be associated with the element. The neutron will be whatever's left over. This is different than if I was to write something like this. Actually, let's do like kind of a combination one. So let's say we're at chlorine. No, I don't want to do chlorine anymore. I'm going to do magnesium 14. And I'm going to put it that it's charged. So this is written a little differently than this guy. I want you to tell me protons. I want you to tell me neutrons. And I also want you to tell me electrons for that.
Miss Henderson, when you ask us to like do these, do you want us to like send you things like direct message, like what we get, or just to practice them and write them in our notes?
Oops, sorry. No, you don't have to put it in the chat or anything like that. We'll just go over it together. Yeah.
Okay.
Yeah, I'm not quizzing you guys on any of this stuff in that capacity. Okay, so this one is kind of a little bit, there's a lot going on. So it's determining what is talking about what where. So I'm gonna do a color coded thing here. So if this is magnesium, the 12 here, those two things correlate to each other. This is the atomic number, it's magnesium, that has to do with the protons. So I'm gonna put 12 protons here. The number of, sorry, I did one thing incorrectly here. My bad. We want that to be 24. It's like 12, that would give us 2 neutrons. That doesn't make sense. So the number of neutrons are going to go off of this 24 here. So 24 minus the 12 will give us, in this case, we have 12 neutrons. The number of electrons for this, we'll use black. This here, well, 2 plus is going to equal the number of protons, 12, minus whatever my electron value is. So rearranging this equation, electrons should equal a value of 10. So seeing how these, different things are talking about different places or different particles. Okay, so back to that, like, why is it a decimal thing? A really good example of one that has a pretty hardy decimal is chlorine. So when you look at chlorine's atomic mass, it's 35.453. Like some of the masses, for instance, hydrogen hydrogen's mass is 1.0079. It's so close to 1, we usually can just call it 1. Most of the isotopes out there are hydrogen with just 1 proton. Chlorine, though, has that mass of 35.453. It's like right between 35 and 36. And so we can't ignore that when doing calculations later on in the semester. But where did that 35.45 come from? Well, chlorine with an isotope 35, which actually has a mass of 34.97. Sometimes in these problems, they will say it's chlorine 35, and that's all that they give you. Just use 35 as your multiplying value. If they give you a more specified mass, use this number instead of this number, okay? So 75.77% of this chlorine is chlorine 35. A majority of it is chlorine 35. The remaining 24.23% is the heavier chlorine 37. So just conceptually, like, because more of it is the 35, I'm going to expect the mass to sit closer to the 35 than the 37, right? It's going to be somewhere in between. We're going to average them out, but I'm going to expect it to be closer to 35. What some people like to do here is they go, well, can't we just add the two masses up, or, you know, the more specified numbers? Can't we just add the two up and divide them by 2? No, because they don't have the same weight, right? This makes up a bigger percentage than this. So when calculating this, we need to take our mass of each isotope and multiply it by its weighted percentage. The percentage needs to get out of percent and into decimal. So we would move this decimal over 2 places, or we would just divide the value by 100. It's the same thing. So that's where this number is coming from. Do you see this 0.7577? That is its percentage value. So that is this thing right here. The mass is, they're using the specific mass. So you multiply those two values together for isotope 1. And then you add it to what you've got going on in isotope 2. So here's the percentage for isotope 2. And here's the mass for isotope 2. And this is isotope 2. So you take this and you add it to this, and this is the value that we get. How I know that this is correct? Well, it looks really lined up with what's happening on the periodic chart, right? Another thing, this number sits somewhere between 35 and 37. That makes sense. If your value has like skyrocketed to like 100, you have no longer averaged your values. You have done something else. So there is a specific formula for this thing on the next slide here. You take the fraction of isotope 1 and you multiply it by the mass of isotope 1. You add that to the fraction of isotope 2 multiplied by the mass of isotope 2. And you continue that process for however many isotopes you have. I probably won't give you a problem that has more than like 2 or 3 isotopes, okay? But there are some materials out there that have like 10 isotopes, and so the process gets longer. This fraction of the isotope, this thing is the percentage put into a decimal form. Because what is percent? When we say the word percent, per 100. Exactly, per 100. So we're just getting rid of that per 100 and getting it into its true decimal value by dividing it by 100. So we look at this one here. We've got gallium, which has 2 naturally occurring isotopes. There's gallium-69, which actually has a mass of 68.9256 if we're going to be very precise. So we're going to use that. And that's natural abundance is at 60.11%. Okay, so a majority of it is this gallium 68.9256. Then we have gallium-71, which actually has a mass of the 70.9247. So we're going to definitely want to use that value. And its natural abundance is the remaining 39.89%. Calculate the atomic mass of gallium. So we're going to take the fraction of isotope, the decimal fraction of isotope 1, and multiply it by its mass. So instead of being at 60.11%, we want to move that decimal over 1, 2. This we're going to move over 1, 2. We're going to take this value times this value and add it to this value times this value. So let's look at kind of, they take the pathway through the slides here. So they've gotten the decimal out of, or the rather the percentage out of the fraction and into the decimal. We just move the decimal over 2 places. It does the same thing. Then we're going to take that, multiply it by its mass, and then add them together. And we get 69.72 for gallium, which, you know, if I reference the periodic chart, yeah, close enough. Mine says 69.723. And so that's how you do that. So I want you guys to do one of these on your own. Okay. So I'm going to have you all do the first one here. It says rubidium is a soft silvery metal with two abundant isotopes, rubidium 85 and rubidium 87. If the abundance of rubidium 85 is 72.2% and the abundance of rubidium 87 is 27.8%, what is the average atomic mass of rubidium? So this one doesn't give you a specified mass, like a really detailed mass. So just use the 85 as your mass for this one and use the 87 as your mass for this one. All right. So I'll give you all 3 minutes to work through that one, and then we will go through it step by step. Okay, so it's going to be, we want to take our percentage and move it into decimal form. So over 1, 2, 1, 2, 0.722 times the mass. And in this case, it's really simple. We're just going with the 85. I'm going to put this in parentheses so I can know that this is something I need to do first. We're going to add that to the second isotope, which has a weight of 0.278. We're going to add that, or rather multiply. And multiply that by the 87. And we parentheses it out. So, you know, it may serve you just to be able to calculate them individually. So 0.722 times the 85 gives you a value of 61.37. And then we're going to add that 0.278 times the 87 gives us a 24.186. Add those two values together. And we get 85 point, I go with 1 decimal because the percentage is in decimal. So 85.6 is your mass, and this is AMU. I mean, you can check it off on the periodic chart. 85, mine, on the periodic chart, mine's 85.46. Make sure I did that right, 0.722 times 85. Yeah, it's just rounded a little heavy with the masses. So that's how you do that. Any questions on calculating mass? On the average of mass, on where those numbers are coming from? Yes, no. Okay. So sometimes students will be like, oh, well, I'll just look at the periodic chart, right? And I'll just write whatever that value is down. Sometimes they're hypothetical elements. So they could say, hey, a hypothetical element has these different masses with these different percentages. What is its overall average mass? And then you can't like check the periodic chart. So definitely understand the concept on this. So that is the end of chapter 4. I think it talks one last little bit. Oh, share my screen with you. About the difference between stable isotopes and radioactive isotopes. So some isotopes from a given element are unstable. Like when a lot of times when they have a lot of neutrons packed in them, it makes the nucleus relatively unstable. So it gives the material a lot of energy. It wants to decay. So whenever you hear about like nuclear radiation or radioactive material or radioactive isotopes, what they're talking about is an atom that has an unstable nucleus that wants to decay into something more stable, and in the process releases a bunch of energy. There are also isotopes out there that are stable though, a lot of stable isotopes, and they won't degrade or change. So nuclear radiation can be harmful to humans and other living organisms because the energetic particles that are given off from the radiation interact with biological molecules. Yep. Hello?
Do those numbers make it down into scientific notation from the previous slide?
Yeah, I'm not too anal about that.
Like written out into scientific notation, is it that big?
Yeah, I'm not too anal about scientific notation when it comes to calculating those. I would just go with whatever the decimals are that you have. So like if your mass only has like 2 decimal places or 1 decimal place, just go with that. But I won't give you, like on your test, there won't be 2 multiple choices. where one of them has like you've solved that problem, and one of them has 2 decimal places and one of them has 3 decimal places. It'll just be right or wrong. You'll be able to differentiate it pretty easily. So, okay. So yeah, radioactive isotopes, they're not always harmful. Sometimes they're beneficial. They use radioactive isotopes in a lot of medical treatments like radiology. They'll give you some sort of radioactive material, you'll ingest it, or they'll put it into an organ, and then they'll stick you in a big machine and they'll pick up the radiation that's giving off, and it can give us more specific imagery of soft tissue. No. All right. We are done with chapter 4. So that covers everything that will be on your first test. All right. We are in a good spot. So I'm going to lecture a little bit ahead. So then we'll still get out early today, and then we'll probably be able to get out a little early next week as well during lecture if we start chipping away at it. But know that anything that we're going to talk about from this point forward is not on your first test. This will be on your second test.
I'm having connection issues.
Okay, hold on one second.
You're coming through broken.
Okay, give me just a second.
Coming through broken.
Yeah, let me see if I can mess with it. Okay, is that better? I'm like in the back, towards the back of the house, so I have an internet booster, and sometimes it works and sometimes it doesn't. You guys able to hear me?
Yes, ma'am.
So Will's like sort of. Okay.
Yes, ma'am.
Hold on one second, I might move places. All right, I moved into a different space. Is that better?
Yes, ma'am.
Yeah, okay.
Yes, ma'am.
Pesky internet. I need my pen. Yeah, okay. So the last chapter, we were talking all about elements and individual atoms. Now we're going to get a little bit more complicated. So we're going to start to put those things together into molecules and compounds. Because most of the things that we interact with in our everyday life are compounds. Occasionally we deal with elements, you know, if you have like a platinum ring or something, but even those are usually mixed with something else. So here we've got an image of sucrose, sugar, and sugar is a combination of carbon, hydrogen, and oxygen. The sugar molecule and the properties of sugar are very, very different to carbon or hydrogen or oxygen. You would never eat like a hunk of carbon on its own in the form of graphite or a diamond. It's only when it comes together in this very specific ratio and this very specific ordering that it then takes on the properties of sweetness or sugar. Another example, sodium and chlorine. So sodium over here on the left is an extremely reactive metal. It tends to dull very quickly when it's exposed to air. On the right, we've got chlorine. Chlorine is a yellow gas that smells really gross, and it's also poisonous. So both of these things are kind of unappealing, but when they come together, we get sodium chloride, which is table salt, which is like the universal seasoning. It's what makes our food taste good. This has completely different properties than the individual elements that it's composed of. So that's a good thing to start wrapping your head around, is just because it contains something doesn't mean it has those properties of its elemental form. So just because it contains sodium doesn't mean that it has this like metal-like property when it's in its sodium chloride form. So some of the substances we encounter are elements, but mostly what we encounter are compounds. Free atoms in general tend to be relatively rare in nature. Why are they rare in nature? Because elements outside of the noble gases, which is column 8, elements are just reactive buggers. They're not satisfied. They're not happy in their own state. So they want to bond together with other things to form a more stable electron configuration. A compound is different than a mixture. Remember, in a mixture, we can adjust the proportionality, right? So salt water, I can add more salt, I can add more water. Salt itself has a chemical formula of NaCl that I cannot change. If it is going to have the properties of salt, it needs to be a 1 Na for every 1 chlorine. So compounds are fixed proportions and bonded together. Mixtures are a variety of proportions and they aren't fused together. On the left here, I have a balloon that is filled with a mixture of oxygen and hydrogen. I could technically put more hydrogen in there. I could technically put more oxygen in there because the oxygen molecules and hydrogen molecules aren't fused or bonded together. They are just occupying the same space. On the right, I have a compound. This is a balloon filled with water. It also has hydrogen and oxygen. How is it different from the mixture? The hydrogens and the oxygens are bonded together as a molecule or a unit. I can't change the ratio of hydrogen and oxygen here. If I add more water, the hydrogen-oxygen ratio will stay the same. 2 hydrogens for every 1 oxygen. You need something? Your phone? Sorry, I had to take over my husband's space. Okay. So there is a statement that Proust came up with that when we make a compound, any sample of the given compound has the same proportions of their constituent elements. So if I have a single molecule of water, it is 2 hydrogens for every 1 oxygen. If I have a bathtub filled of water, it is still, the proportionality will still be 2 hydrogens to every 1 oxygen. That proportionality is consistent no matter how big the sample is. Our sample could get as big as the ocean, well, I guess not the ocean because that's a mixture with salt water, but let's say it's as big as a swimming pool and it has pure water. We're going to have 2 hydrogens for every 1 oxygen. The mass ratio of all of the elements, no matter their size, is also constant. So the mass ratio between oxygen and hydrogen in water is going to be a mass ratio of 8:1, or 8 grams of oxygen for every 1 gram of hydrogen. Again, that won't change depending how big the sample is. If your sample is, 18 grams of water, it'll break down to 16 grams of oxygen and 2 grams of hydrogen, or it'll reduce down to that 8:1. It'll always reduce down to that 8:1 ratio. This ratio, though, is only true if we are dealing with water. If we're dealing with, like, let's say ammonia, which is NH3, its ratio is 4.7:1. I'm not expecting you guys to have these memorized or anything like that, but just know that the mass ratio will also be consistent. So when we're writing a compound, we have to be able to, like, consistently tell people, because there's so many compounds, there's thousands and thousands of compounds. So we want a really specific way on how we write a chemical formula. So a compound is represented with these chemical formulas, and they always follow a similar pattern, and that is that we use the symbol. So here's H2O. We use the symbol for the elements that are present, and we use subscripts to tell us how many of each of the atoms are present within that specific compound. So when looking at water, H2O, the 2 is telling me that I have 2 hydrogens. There is no 1 written here. It's an inferred one, but I have 1 oxygen. We would just omit it. If I'm writing the symbol, I have 1 of them. So here we go. We've got 2 hydrogens and 1 oxygen. Elements that aren't present are not written. So I don't write magnesium or sodium or aluminum here because those aren't involved in this compound. You think of this as a recipe, okay? This is the recipe for water. Here are some other recipes. Sodium chloride, NaCl. This is a ratio of 1 sodium to 1 chlorine. CO2, carbon dioxide. This is 1 carbon for every 2 oxygens. Here's table sugar. This starts to get a little bit more complicated, and these start to get, kind of scary looking, but it's a similar idea. I've got carbon, hydrogen, and oxygen present. There are going to be 12 carbons, 22 hydrogens, and 11 oxygens. It's a big molecule. This is an example of an organic molecule. They tend to get much clunkier, much bigger. So important thing, we never want to change subscripts just for fun. We always want to honor the subscript that is associated with that given compound. This is a perfect example. Here is CO and here is CO2. Sometimes people will go, oh, well, I don't want 2 oxygens. I just want 1 oxygen. So I'm going to write it as CO. That's like roughly the same thing, right? No, it's definitely not. This is carbon monoxide over here. This is a pollutant. This is carbon dioxide. This is a relatively harmless gas that we exhale and plants inhale in their respiration process. So just by changing out 1 carbon, we have totally different properties. We definitely do not want to just, ditch subscripts because then you have a whole new material. When we're writing a chemical formula, you want to follow the rule. This applies like 98% of the time, but you're going to write the most metallic element first, followed by the least metallic. So sodium chloride, or the formula for table salt, is NaCl, not ClNa. When I'm looking at this one just kind of looks weird, but you may not, have had enough chemistry to have that sort of be a natural thing for you. So you're just going to go off the fact that this is a metal, this is a non-metal. So we write the metal first, and then we write the non-metal. In compounds that don't include a metal, you want to list the most metal-like thing first. And when I say most metal-like thing, I mean the thing that's closest to the zigzag line. So here's a periodic chart here. Here's our zigzag line. So the closer we are to this thing, the more metal-like we are. So let's say I have a combination of nitrogen and oxygen. I would want to list my nitrogen first, and then I'll list my oxygen. The nitrogen comes first because it is closer to the zigzag line. Same thing with, I think when they talk about sulfur and oxygen, I always list sulfur first and then oxygen because sulfur is closer to the zigzag line. Are there exceptions to that rule? I mean, all these rules, there are exceptions every now and then, but they follow, you know, again, for the most part. So we write NO2 and NO as opposed to O2N or ON. We write SO2, not O2S. Here is the ordering of things that are most metal to least metal-like. So carbon is more metal-like than phosphorus, then nitrogen, hydrogen, and so on. Fluorine is the least metal-like. You can memorize this, or just, again, if you work off the zigzag line, the things that are closer to the zigzag line are more metal-like. The things farther away are less metal-like. One big exception to that is this guy right here, this thing called, this is hydroxide. Hydroxide is an OH with a minus charge. The O gets listed before the H does. Okay, so that thing, that OH thing, what was that? That is called a polyatomic ion. Polyatomic ion tends to freak people out. Like, what does that mean? Well, let's break it down. So poly means many, like polytheist or polygamist, many gods, many wives. So it's multiple atomic atoms, many atoms. And those many atoms are together to form an ion. So it's a packet of atoms that has an overall charge to it. This right here is a great example of a polyatomic ion, NO3 minus. This thing is known as nitrate. Still having connection issues. Yeah, I don't know what my internet is going on today. We're just going to roll with it. The recording should hopefully be clear. So if you guys need to go back and check on stuff, you can look back that way. So this guy right here, this is nitrate, NO3 minus. So what is happening is we have one nitrogen. It's combined with 3 oxygens, and the whole thing has an overall -1 charge. Keep the numbers on the bottom and the charges in the upper right-hand corner separate from each other. Don't mishmash those together. The negative doesn't come down to the 3. The 3 doesn't go up to the negative. Those are in different spots. This is a superscript. This is a subscript. Subscripts tell us atom numbers. Superscripts tell us charge. So a lot of times when we have polyatomic ions, we have to multiply them, or we have more than one of them. So we would put them in a set of parentheses like this thing here. This is magnesium nitrate. When looking at this thing here, I have to put this in parentheses because I have 2 of these nitrates. So when I'm adding up all of my individual atoms, I need to multiply the subscript outside of the parentheses by whatever the subscript is within the parentheses. And this gets distributed to both materials. Okay, so the 2 is going to get multiplied by the 3 for the oxygen to give us a total of 6 oxygens. And the 2 is going to be multiplied by the nitrogen. There's only 1 nitrogen to give us 2 nitrogens. Okay, and then the magnesium doesn't have any parentheses and it doesn't have a subscript, so we just have 1 of those. So we want to get in the habit of seeing this parenthesis and the number outside the parenthesis as a multiplier of what's ever happening inside the parenthesis. Let's do another one of those. I'm gonna write out, let's do aluminum sulfate. So Al2SO4, 3. I want you to tell me how many of each atom we have in one of these molecules. They contain aluminum, it contains sulfur, and it also contains oxygen. I'll give you a minute and a half for that. Okay, Brittany said her screen went blank. Is anyone else having that problem? James, do you have that problem? I can see your face, that's why I'm asking you. Gosh, the internet, man, it is just not working today. You're not having that issue, okay. All right, we're gonna roll through just a little bit more. And then
Mine is fine.
You're fine, okay. Okay, that might be an individual thing then. It's lagging. Can't hear me. Ugh. Internet. All right, I think we're gonna push through this right here, and then we're gonna call it for today. I'm just gonna call it. Get out early. Okay, so we've got aluminum sulfate. When adding up the number of atoms of each, aluminum we should have 2 aluminums, right? That one's pretty easy. There's the 2, talking about that guy right there. So 2 aluminums. Sulfur, well, I've got this 3 sitting outside the parentheses, so I need to distribute it to both of them. So I'm going to take the 1 sulfur inside and I'm going to multiply it by 3 for a total of 3 sulfurs. The oxygens, I'm going to take the 4 oxygens inside and I'm going to multiply it by the 3 for a total of 12 oxygens. Yes, there are 12 oxygens here. So if I was to draw this thing out, it's sulfur with 4 oxygens. But if I have 3 of them, right, it looks like this. All right, there's the 3 sulfurs that we see here. 1, 2, 3. The 12 oxygens are 1, 2, 3, 4, 7, 8, 9, 10, 11, and 12. That's where it's coming from. So 3 of these, 1, 2, 3 of them. Okay, that's kind of visually what's happening. All right, so we'll call it for today. Make sure to get your test done. I'm gonna try and fiddle with the internet. hopefully we'll have better connection next week. Otherwise, enjoy your weekend. Do something fun. Alexis, I'm not sure what your question is. Stay around and we can chat after class, okay? Great, so you guys are good to go. If you have any questions, email me. Otherwise, we can try and stay around and see if I can help you out one-on-one. I'm gonna move into my dining room here and come with me. But if you're good, I will see you next week. Bye, guys. All right, so you guys have general questions, or because you're good to go if you don't, or if you have personal questions, you're good to go.